Okay, so I think we're going to try to wrap up chapter 8 today. We still have 8, 7, and 8, 8 to go. So, what do we have in these chapters? 8, 7 is where we're going to use the tables that I mentioned several times throughout the course. Um, if you look in Brightspace, you'll see that there is posted there somewhere. Let me just go find Brightspace. I got so much stuff open. Um, wow, I do have a lot. All right, that's all right. I'll just open it up again. Anyway, so there's quite a few tables in there, one of which is the gigantic integration table that has pretty much every rule there is for integration. And as you can imagine, it's quite long. In fact, it's about 3 pages of tiny little print. So let me show you where that would be. I also just recently added a table of what are called double angle and half angle formulas. These are trig formulas that could come in handy. They're often used for reducing the complexity of a problem. So let me show you what I'm talking about there. Here we go. So here's the tables. And the one that down here that says integration tables, there's actually one up here with the simple or basic rules of integration, which is great. It's a great table. But it only can have so much on it. There are limitations to how many rules are on here. So these are the ones that the book calls the basic rules of integration, which are the ones that aren't too overwhelmingly complicated. They involve the basic trig functions, e to the u, that kind of thing. And then we have the full version, which is enormous. Um, yeah, look at that. It's a lot. Okay. So now they're going to ask us to use this table in several times in this section to identify the correct form that we need. And this can take a while because there's so many of them. You can see they're numbered, and there's 100 of them here. But this is the the one I just added today because I thought it could potentially come in handy if you do run into a very messy trig expression. Sometimes it's possible to simplify it with these double angle and half angle formulas. Okay. And so very occasionally, you'll find these very useful. I think we'll need some of them today. Okay. So, all right. So what do they want us to do? So by the end of this section, you should be able to find an indefinite integral with a table of integrals. Then we're also going to learn about reduction formulas. And then we're going to find the indefinite integral involving fractional expressions, which is where the double angle and half angle formulas will come in of the sine and the cosine. So in small stages, they're trying to cover as many different integrals as possible. Now, of course, we still can only do so many of them. You'll see more advanced ones as you get further and further into your calculus courses. But here, we're trying to cover as many of them as possible. So we'll start with the tables. Now, the tables are meant for cases when we can't use any of our other rules that we've learned so far, because sometimes you just don't know what to do, and you look in the table and you might find something that helps. So here's one. Look at this disaster. Well, we're not going to be able to use some of our other techniques with this one. So what we have to do is go through the tables and see if perhaps there's something in there that is a little bit more down to earth. Okay, so let's copy this in here. And so what they're going to say is, well, if you were to look in the table, consider forms involving radical a plus bu. Whoops. So now it looks like the one they have in mind is this one. It involves arctangents. So where exactly is that? in our table, by the way. Let's go back and find that. All right, here we go. So they're suggesting we look for 1 over u. To see what I mean, look how messy this is. 1 over u radical a plus bu. Oh, there it is, number 17. That's right, isn't it? 1 over, yeah, right there. Look at that. So, what they are telling you here, as you can see, is that there's two possibilities depending on the sign of A. So it turns out here A is negative. If you use this identity, I guess I can't copy it. All right, let me just write this down. Oh, actually, this, I mean, this is it right here. I guess we don't have to copy it again, but the important detail is that this assumes that A is negative. Otherwise, we have that other horrendous expression. Look at that thing. Okay, so the thing is, how do we get from here to here? So the recommendation is if we let A be -1, B is +1, and U is X, then we have which dx, which we could rewrite as, and that is in fact, let's copy this down here, what we have. Now, I don't know about you, but I don't think that was the least bit obvious. I mean, it's going to take a lot of practice to start recognizing some of these, but it is true that this is in the right form. And so therefore your answer is right here. And so again, keeping in mind that what we're actually integrating is here. And that means that we have these three expressions. U is A is -1. B is +1. U is X. Well, now we can directly substitute and find what we're looking for. All right, and then we can simplify it a little bit. And so we ultimately end up with 2 arctan radical x minus 1 plus c. Oh God, what an ordeal that was. But we got it. Okay. But really, it could have been a long time. I mean, it wasn't that obvious, I think. The only way, I mean, if you notice that this is a product of some term times the square root of something under here, that would help. But it will take a lot of practice to get to the point where you recognize these right away. Now, the reduction formulas are cases where we can take a horrendously complicated integral and break it up into a function plus another integral, where presumably h of x is easier to sorry, integrate f of x. Otherwise, there's be no point in doing this. So here's some suggestions. Let me copy these into our notes. Now, I didn't actually notice these in any of the charts. Maybe I didn't look carefully enough. Hold on one second. Radical u sine u du. Maybe it is in there. Let's go look. What was it again? Radical u sine u. There it is. Ah, I guess this is the area that they're talking about. Formulas 52, 3, and 4. Yeah. Okay. So those are the formulas that they have here. Okay. But, it doesn't list them separately. It doesn't identify them as reduction formulas. I guess we're supposed to figure that out ourselves. All right. So again, let me just copy these real fast. All right. So let's see what examples they have. X cubed sine x. So that would be u to the n sine. That would be this first one, of course. So let's copy this. And so that implies that u is x. Oh, wait a minute. That can't be right. You know what? It's got to be the second one because this first one doesn't have an exponent. All right, let's get that out of there. Here we go. So yeah, that's good. That means x can be u, n is 3, and then, yeah, that's right. All right, so we still have to deal with this one, but we have part of it. And oh, I see. Okay. So then this piece by itself requires another of these reduction formulas. Which one is this? This is u to the n cosine. Yeah, this one. So then in this case, we would have u is x, n is 2. So we keep the 3 on the outside. So now n minus 1 is just 1. Okay. So I can see that we're going to have to be careful not to lose track of what we're doing. So we need to bring together this result. I'll tell you, let's copy this. I can easily see something getting lost with all these parts floating around. So we just discovered that this part can be replaced with this. So when you bring them together, you'll have that plus x squared sine x. So this integral, but that's not right. We need, I just realized I left out the three. Yeah, that three here. Again, it would have been so simple to miss that. So that means, yeah, okay. Then we can distribute these. And I believe they gave the impression that Formula 52, let's see what this one is. Oh, it's the first one. U sine U. Okay. So that means this piece, of course, this means that U is X, and that's all we need. We're going to have, and then we'll have, and of course, that has to get added to these two. So the overall answer, the original integral was x cubed sine x dx. So we already have the first two parts of it, minus x cubed cosine x plus 3x squared sine x. And now we just add on the rest of this. And at long last, we're done. Oh my God. What a disaster that was. Okay. So yeah, I mean they like to throw these hard ones at us right off the bat. It's slightly in a different order, but it's there. Okay. So this one required not just one but three reduction formulas. So that was a bit much, but there it is. Okay. But we managed it. Now, fractional expressions, these are the ones that are going to involve those identities, the half angle formulas, the double angle formulas. So, like with this one, as soon as you see that sine 2x, you're going to be suspicious about whether or not we need one of these. In fact, we should probably copy that down right now. Sine 2x or 2 theta, whatever. is would be 2x cos 2 sine x cosine x. Okay. Oh, one thing. I just want to make sure I don't forget about the page numbers. All right, that's good. All right, so one of them is that the sine of 2x is 2 sine x cosine x. Okay. And of course, there's others if we need them. So for this problem, what do we have? So it looks like they're suggesting that we rewrite this a little. And then, well, of course, we can factor out that too. And then, I don't know if they need us to do it again. Oh, huh, that's strange. That's the end of it. Oh, wait a minute. No. No, they're saying that we need another rule. All right. And so it says here that a check of the forms involving sine u or cosine u shows that they do not apply. So consider forms a plus bu, like this one. And then what would we do about u? So they're suggesting we let u equals cosine x. I guess that's because it's in the denominator. I guess that would make sense because we're trying to find a plus bu, which means that a is the 2 and b would be 1. There would be an implied 1 there. Oh, all right. So then I guess we're going to apply the rule directly. Wait a minute. Hmm. See, then they're having us rewrite it again. They're putting a negative outside. Oh, I get it. You know why? We need a du because remember the derivative of the cosine is negative sine x dx. That's what this is all about. So if we let this be u, this can become our du. And then in the denominator, we have still 2 plus cosine x, which is u. So let's see, we have, and then, and again, remember that a is 2 and b is 1, and of course, this is cosine x. So according to this rule, So we have, and of course, U is just cosine X. All right. Oh, I forgot about the -2. There you go. That'll do it. All right. Much better. Okay. So yeah, it's fine now. All right. What other? Okay. So let's see. What is this one? So if you look at the double angles, actually, this is one of the half angles. At first glance, you're like, what's going on here? But way down at the bottom, oh, that's interesting. It's one minus one over cosine theta over one plus. Huh. So I guess what they're having us do is take this expression and rearrange it to solve directly for cosine x. But then they don't go any further with it. Okay. But all right, so that's that. All right, so now we're going to look at one of the tables and see what we can come up with here. Now, if we get lucky, it'll be one of the straightforward ones. So it's going to be something like, something along those lines. Let's see what we can come up with. Oh, not this one. Oh, here it is. Okay. So, the one we were hoping to find looks something like this. Oh, I think we're getting close. I think it might be this one because it allows a plus and minus. Um, But we do need to have something like this. No, it's got to be one of these. All right, let's try this one. 35, 1 over e squared. But then if that's the case, then I think what we're going to have to do is u would have to be 6x. A would be 5. So that u squared would be 36x squared. All right, so here's what we're going to have to do. We'll have to rewrite this. We need a 36 that we don't have. Oh, yeah, and then du is d6. Okay, 60x. Now, unfortunately, that's not what we have. So what we're going to have to do is rewrite it slightly. The original expression, we need to supply the 36. So since the 36 is in the denominator, we could just multiply out here by 36. Okay, that's good. But we still need a 6 for this dx. So I'm going to fix it one more time. I'm going to multiply and divide by 6. 1 over radical 36x squared minus 25. And then here I'll have 6 dx. And again, we defined u to be 6x, du is 60x, and then a is 5. So, and then they're telling us that the solution is right here. Actually, I'll copy it from here. It's minus and plus. Now, if you notice how it's minus and plus instead of plus and minus. So it's the opposite of whatever's going on inside this radical. So therefore, it would be inside the radical, we're subtracting. Therefore, this becomes positive u squared minus a squared. Sorry, 25. Or I could write it as 5 squared. And then we have a squared. All right, but these sixes cancel. All right, let's see how we did. Very good. All right. So the tricky part was recognizing that not only was that the right form, but that we would have to make a substitution because it wasn't actually what we needed. We just supplied a constant, but we've done that before. So it was kind of a lot of steps, but we did it. All right, I shudder to think what the next one is. Um, is improper integrals. And really all that means is that one or both of the limits of integration are either positive or negative infinity. So the rules are different when that happens. So also they're going to show us what to do in case there's a discontinuity in the function that we're integrating. All right, so why don't we begin at the beginning? Here's our traditional definite integral, which is defined by the fundamental theorem of calculus, and we know exactly what to do here. So we're going to evaluate it over that interval. Let me just put this in here. So first we'll start with a proper integral, the one that we're very familiar with. And so we know that how this works according to the fundamental theorem of calculus. You just evaluate the integral and then solve at b and at a and subtract. All right. But now what happens though? Now, of course, remember, like always, there's assumptions being made behind the scenes of any mathematical theorems that we might have. This one is based on the assumption that the function is continuous over that entire interval from a to b. So what we're trying to do here is see what happens when that's not the case. Either that or when the integral, the limits themselves are either positive or negative infinity. For example, um, and by the way, those are known as improper integrals. So if we have a infinite discontinuity at c when either from the left or the right, the limit as x approaches c is either positive or negative infinity. For example, f of x is 1 over x. So clearly, as x approaches 0 from the right, the function is converging to infinity. And over here, as we approach zero from the left, the function is approaching negative infinity. So these are referred to here as infinite discontinuities. Okay. Now, once we've established that, they're going to show us this example, which looks pretty straightforward, but it turns out that what's going to happen is that instead of using the traditional approach that we've been using, we're going to need limits. Okay. So let's take a look at this one. All right. So we know how this works. Let's say you have, I'll rewrite it like this so it's easier to see that we're using the power rule. Our old friend, the power rule. So we'll have x to the minus 1 over minus 1 evaluated between 1 and b. So I'm going to factor out the negative. And I'll tell you what, let's rewrite it as 1 over x. So you end up with negative 1 over b minus 1 over 1, or 1 minus 1 over b. Okay, so whatever b is, that's going to be our integral, or the result of our integral. Now, as we get close to b, sorry, b gets close to infinity. So here's what this thing looks like. This is part of the function 1 over x squared. This is the first quadrant only. And so the integral over 1 to b is simply that shaded region. Okay, but if we continue to push that shaded region out to the right, how do we figure out that one? Well, what we have to do is take the limit of the upper limit of integration b as b goes to infinity. And so you can see that if I took the limit, okay, so now if we take the limit as b goes to infinity of this expression, now, of course, the limit of 1 is just 1, but the limit of 1 over b as b goes to infinity is 0 because you have a number that's getting extremely large in the denominator with a constant in the numerator. So the final result is 1. So in other words, this integral has a solution of 1. Okay. Now the graph shows you what just happened. If we start at 0 and we go all the way out to infinity, what they're telling us is that the area under this curve is exactly equal to 1. All right. Now, of course, in the past, we only were interested in finite intervals. This is the first time we're seeing this done with infinity, and so that's why we need to change the approach a little bit. All right, so let's see what else. Oh, wait, I think I skipped one. Here's one. Let's try this. 0 to infinity, e to the minus x dx. And again, there's the graph. And it looks a lot like this one, doesn't it? Yes. Okay, it's a curve, and we're trying to find the area from 0 to positive infinity. But of course, that requires an improper integral. So that's why we have to take the limit of the upper limit of integration. Let's see what we get here. Instead of 1, oh, actually, just by ridiculous coincidence, it's also 1. But all right, let's see how we got there. So first things first, let's remind ourselves if this was an indefinite integral, we could solve this with u substitution. U would be e to the minus x. Sorry, it would be the minus x. just minus x. Du would be negative dx. So that means we have to supply a negative here to make this work. Okay, so now we're good because what we have here is negative integral e to the u du, which means negative e to the u plus c. Or, of course, since u is negative x, and that's it. So what's different over here? Okay, so using this result over here, you can see that we'll evaluate it from 0 to infinity. And then, of course, we'll have to take a limit. Let's move this negative outside. Substitute. We're going to replace, by the way, the infinity with b, and then we'll take the limit. All right. All right, and then we have plus 1. And then, now, of course, we need to take the limit of this to get our answer. Now, of course, the b is in the denominator. You can see that's the exponent, so we're going to wind up with 0 plus 1, which is just 1. Okay, great. And of course, yes, you can see the graph right here. This time, the area is equal to 1 as we go from 0 to infinity under this curve. Okay, now you knew this was coming, a trig function. Let's try this. Now, we do have these tables. Okay, you can see this one you could probably find on the basic trig tables. I don't know if I have that one open. No, yes, I do. Well, no, it's this one. Okay. Um, let's see if I can go find the basic table. All right, here we go. And we'll see if that one's in there. Okay, basic rules. Yeah, it'll be much easier to find it here. There's only a few rules. So 1 over um, x squared plus 1. Oh, maybe not. No, I don't see it there. All right, let's look at the other one. Oh, but then it wouldn't be x squared, it would be u squared. Okay, let's find that one. All right, hold on. Oh, I know it's here. It's one of the, yes, of course it's an arc. Where are they? So we're looking for 1 over u squared plus a squared. Oh, there it is, right there. Okay, number 23. So I guess it wasn't on the basic tables. All right, let's write this down. So, um, whoops, 1 over a squared plus u squared du equals 1 over a arctan u over a plus c. Yep, that's it. So in this case, okay, clearly u is x, a is 1. Oh, and of course du is dx, so we're good there. 1 over 1 arctan x over 1. So it basically ends up just being the arctan of x. Okay, so now of course we're doing it though with an infinite limit of integration. So of course, when we do this, we're going to wind up evaluating this between 0 and infinity. And of course, we'll have to take a limit. The arctan of 0, ooh, let me get out my calculator. So remember what that means. The arctan of 0 means the angle whose tangent is 0. All right, let's find out. Now, your calculator does have these functions on the top of the trig buttons, if you can just about make it out there. The second of the tangent button is what you're looking for. So you put second tan, you'll hit second tan 0, enter. And it's 0. Well, that's good. That's easy, nice and easy. Okay. So we have um, the final result is arctan infinity. Now, of course, we're not actually solving it. Actually, I should have replaced this. This should become a b. And so we're going to take the arctangent of b, but the limit. So that should give us infinity. Um, well, no, it doesn't. It says here that it's pi over 2. That's interesting. Let me just check something out here. Oh, you know what? I think I know what happened here. The tangent of pi over 2 is undefined. Okay, that explains that. Okay. So in other words, the area under that curve is pi over 2. All right. So up to this point, all we've had to deal with was One of the limits of integration is infinity. What they want us to see now is what happens if there are discontinuities. These are also referred to as improper integrals. And so if in the first case we are continuous over a to b, and but an infinite discontinuity at b, then how do we solve this? We take the limit as c goes to b from the left, of, and you notice we're replacing the b with a c. Okay, great. And then, of course, if it's the other way around, and here the infinite discontinuity is at a, well, then instead, we'll get c goes to h from the right. And now this time the a is being replaced with c. Okay. And so this way we can still solve for it. Oh, and just like before, we can break it up into pieces. Um, it's continuous over a to b, but there's some c in that interval at which there's an infinite discontinuity, which where it's understood that c is part of this interval. Otherwise, it would be kind of senseless. So I'm going to put this little symbol here, element of AB, just to make sure it's clear that C has to be in there somewhere. Then we can replace this expression with this. And again, that way we can still solve for it. Okay, so let's see some examples. From 0 to 1, dx over the cube root of x. Okay, now the cube root of x looks something like this. So, oh, it's one. You know what I just realized? That's the cube root. It's one over the cube root. Okay, never mind. In fact, I'll tell you, why don't we go to Symbolab and see what it has for this? It's kind of hard to visualize it. Yeah, so there's definitely a discontinuity. There's an asymptote there, um, where x equals zero. So there's a vertical asymptote. So that means the function cannot, I mean, it has a discontinuity there. So that would be the lower limit. All right, so what do we do? So they're going to rewrite it like this, just so it's easier to see how to apply the power rule. So if it were a um, indefinite integral, this would be our result. So here we have, okay, so the zero gets replaced with an A, and then of course we take a limit. Um, oh wait, it's what did they do? Hmm. So, oh, sorry, it's not infinity because the discontinuity is at zero. But they're using B anyway. All right, we'll use the B. Um, but specifically from the right. All right, let's try this. Okay. Now, of course, if we substitute a zero for B, we'll just end up with 3/2 times 1, which is 3/2. Okay. And there we are. And you can see the graph. You can tell by the graph. I mean, it's hard at first to tell by looking at it, but we can see that the it ranges from 0 to 1, and then this is what we're seeing, and that adds up to 3/2. All right, what about the, oh, look at this mess. So instead of radical, the cube root of x, it's now 1 over the cube of x, which has, as you can see, a vertical asymptote there. So it's integral 0 to 2 dx over x cubed. Wait, no, x equals 3, x equals 0. All right. Now, ordinarily, if we had an indefinite integral, we would have, and that would leave us with x to the minus 2 over minus 2. Or you could rewrite this as, yeah, I guess that's a little bit neater. So we'll have, and now let's factor out the -1/2. And then when we evaluate it, of course, now we're going to take the limit from the right. So we're out of luck because this goes to infinity. So the whole thing is infinity, and we say that the integral diverges.